So at the moment I'm looking at the data from question 2, and what I want to do is go through each of the subgroups separately in separate videos, then come back to the whole analysis, and then we can do the same thing for the second analysis. So I'm just going to start here with the Asian studies. So first of all, a couple of things I'm going to do. I'm going to make sure that I'm looking at the risk ratio, which is actually the prevalence ratio. So I clicked on the button here until I had RR. I'm also going to make sure that I click on the random effects rather than the fixed effects. Random effects implies that we think that there's a number, but it's coming from a distribution, whereas a fixed effect says there's only one prevalence, or there's only one ratio that compares the difference between cattle and buffalo, and we're just sampling it with error. On the other hand, random effect says actually it's a distribution, and when we sample from that distribution. Generally speaking, the random effects assumption is usually thought to be more valid. Then the other thing I'm going to check is that I have these interpretations of the left and the right hand side correct. So remember that this is generally written for interventions, right? So usually where cattle is would be the intervention, and where buffalo is would be the control. Now, most interventions are designed to reduce the number of events. So we would normally expect, if we had data where the intervention was effective, that we would have this group's ratio divided by this group's ratio, and that would give us a number less than 1. And so that normally would favour the experiment. So that would be over here. However, this time we're looking at an exposure. So let's look at how the data should be behaving. So let's look at this one here. Clearly, in this row, we have a higher prevalence in cattle. So the risk ratio is greater than 1. So the risk of being positive is greater in cattle. So that means when the risk ratio is 1, it'll be over here, and what that will mean is that the seroprevalence is higher in cattle. So that's what I have. I have higher in cattle, higher in buffalo. So the way I did that was I went into this little properties button that looks like 2 cogs. I clicked on that, and I changed these labels so that they helped me interpret things a little bit better, because the way they were wasn't really helping me with my interpretation. So again, you can see here, so here's an estimate, and I'm going to click on it. You can see it coming and going. Here's an estimate that is on the left-hand side of the figure. If I go down, that says that the estimate is higher in buffalo, and that's true because we've got 2 positive animals in buffalo and none in the cattle. So the prevalence of the estimated prevalence is higher in buffalo. Now notice here this has got a 0. Well, obviously the data is adding a 0.05 in that point. So, having made those few changes, I'm now going to look at the forest plot, and I'm only going to look at the subgroup for the Asian countries. I like to look at the forest plot using this figure, where I've clicked on this radio button that brings up the forest plot. Don't get confused by bringing up the funnel plot, which didn't come up if I close that. That's what happens. So there's the funnel plot, but we're not going to worry about that right now. We want the forest plot. And the first thing I want to do is look at the data. So what I can see is there are spattering of effects across the other side of the null line, and I'm looking at it thinking all of these studies seem to be having confidence intervals that cross 1, and these larger studies, they seem to be really clustering around 1, so it doesn't really look like there's much difference. And the summary effect measure, it basically includes 1. But then I look down here and I see that I've got a chi-squared for heterogeneity of 24 and a p-value of 0.004, which suggests that this is a very rare event, what we're seeing here, under the null hypothesis. So we might be able to reject the null hypothesis. And notice here I have an I squared. Now what does that mean? An I squared is the percentage of variation that is greater than would be expected by sampling error. So it says it seems that something more, so clinical or methodological heterogeneity, is causing this variation rather than just sampling error. So here what I've done is I've moved over to the Cochrane Handbook. You can see, you can just type in Cochrane Handbook into Google and you will find this document, which is a wonderful document. And what I'm in is I'm in Part 2, Section 9, and I'm actually in 9.5, which is a discussion about heterogeneity, and I've just gone on to 9.5.2. And the reason I've done that is I wanted to show you this interpretation of I squared percentages. So it says here, this I squared describes the percentage of variability in the effect estimates that is due to heterogeneity rather than just sampling error. And you'll see here that we have estimates, and our estimate is between 50 and 90, so it suggests that there's substantial heterogeneity, which is consistent with the chi-squared. But one of the things I notice is there's this really massive effect from this Shafi study. Now, 2 things to notice. It's a massive effect, but it's not having much weight. So if I remove it, it's not going to change the summary effect measure. So this summary effect measure is not going to be sensitive for removing this. However, these heterogeneity estimates are likely going to be really sensitive to that. And you have to admit it looks really inconsistent with the rest of the data. So my thought would be to potentially think about removing that estimate and look at the impact of that. So I did that by clicking on it, and I'm going to look at it again. And look, you see, the summary effect estimate really doesn't change much. But now I have a situation where I could say there really is evidence, no reason to reject the null hypothesis. And this really looks like a spattering of a sampling distribution across studies. So this is a sampling distribution of 1, and I'm getting an even number of studies on the left-hand side and right-hand side, as you would expect. So that's my discussion about this section. I'm not saying that one should always just remove studies that you don't like, but this study really does look unusual. I would go back and have a look at that study and try and understand, is there any reason it might be different? If I was reporting this, I would report both. I would say that this was an unusual observation, and apart from this study, by and large, the estimates that are available suggest that the seroprevalence of cattle versus buffalo is quite similar, assuming that all the studies are of equal evidentiary value. It's not clear, perhaps this is the best, this study that I've suggested potentially moving may be the best quality study there is, so it might be the most important study to include. But that's something that you guys need to consider.